Well, let's do part 3 of the final review. So part 3, final review. Yeah, we'll just for the sake of sanity, we'll put that on there. All right, so rotational dynamics. Let's get into it. We've got tau is equal to I alpha. If it's dynamic, this does not equal 0. We are not dealing with statics. So that means that this alpha is not equal to 0. So we're in a dynamic situation. Now we can take that same situation that we had before where we have our force in and we're multiplying it by 3/4 L for our torque in and our force out times 1/4 here. 1/4 L, and that's our torque out. So altogether, we've got our torque net, and that equals I alpha. And in our situation, in our case, that's our torque in minus torque out. Because one's pointing one way and one's pointing the other way. Now, whether, it doesn't matter. Obviously, we had our force in going here, we had our pivot point here, and we had our out force going there. So let's put our force in like pushing down instead, pushing up on the other side. We can define this direction to be positive, then that means that this torque in is going in a positive direction. This force out is also going in a positive direction, so technically we would do that. So torque in and torque out, minus plus. So really, that's our force out. However, you know what? I did do it correctly. You can go back and look at the other video, but the force that we're fighting is this mg. So yes, I was right. Mg is going in the negative direction. So let's do it like that. And our torque out is that way. Okay, so I'm not always wrong. Sometimes I'm wrong about whether I'm right or wrong. Moments of inertia. I'm going to say it again. Moment of inertia. That's the analog to mass. Okay, so this is rotational mass. This is regular linear translational mass. And the units are in kilogram meters squared. And on the final, I'm not going to make you go through and figure out what I is or have to come up with what I is. So the moment of inertia, will be given. All right. So it'll be given either as an equation like 1/2 mr squared or 1/2 ml squared or something like that. Or it'll just be a straight up number, 400 kilograms meters squared. Okay, so we're going to have something of that nature to work with. Okay, so there's not much more to it. That's all there really is to say about moment of inertia, but inertia itself is really, really important, and it's the desire for something to stay still. So the more the inertia, the harder or more torque you have to put on it to get it to move. Also, if it's just inertia, if it's the moment of inertia, it's torque. If it's just the inertia m, it's force. So, all right, rotational kinetic energy. And you guys are pretty good at keeping things simple, and I love it. I'm going to write a few things here. Delta x or delta s over r is equal to theta. R times F net is equal to tau net. Our work net is equal to F dot dx delta x. Okay. So we're given some omega net. What can we go through and find out, or how can we do all the things? I'm not going to rederive these equations. You can start here and you can go down the list. I've displayed it. We're going to do that, and I'm just going to give you the punchline here. Now we got to square them, and we've squared them, and that's fine. And if you notice, this part is KE final, and we're subtracting off the KE initial. And there's our work net. So really, just like before, our work net is equal to delta, 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 delta. Can I help you? Delta KE. So delta KE, that is our rotational kinetic energy. So what is the, and this is just the rotational form of the work energy theorem, but what is the total work net? If we're going to do both rotational and linear, we have both things happening, a linear situation and a rotational situation, then we have to do this. We have to add them together. And this, let's call it linear. That is what happens when you mix both rotational and linear. You have to have both. Okay, so when you're accounting for energy, you just account for energy. You go, okay, I'm gonna do both. I gotta account for both of them. So what's next? Angular momentum. angular momentum, the symbol for angular momentum, L, that equals I omega. Well, we know that I is in kilogram meters per second, meters squared. I'm sorry. I is in kilograms meters squared. Omega is radians per second, but the ghost of radians does its thing and disappears. And so we're left with kilograms meters squared per second. And nice. So we could say something like I naught omega naught equals I final omega final. What have we just done? We've said that L naught equals L final. Awesome. This means L naught is a constant, or we are conserving angular momentum. Okay, so these are statements of angular momentum conservation. Of course, you can write them in any way you want. You can rewrite that as I naught over I final equals omega final over omega naught. And what did I do? What did I do here? Okay, good, nice work. So yeah, at any rate, I might change. I might change so that I initial does not equal I final. Okay, we may put, there may be changes in I. Okay, so that happens. We saw that in the lab, I platform plus I disk equals our I total. Those things happen, right? You have a child on a merry-go-round. You take the child and the child jumps off the merry-go-round while it's in motion. That changes the moment of inertia. So keep in mind that I doesn't necessarily stay constant or the same throughout the equation, throughout the problem, I should say, throughout the problem. Okay. I do an example in the review. I'm going to skip the example and we're going to go, we're not going to go sideways, I hope. We're going to go here to rotational impulse. So rotational impulse equation. I'm not going to write down the other impulse equation. You guys should know it. Okay, well, I did write it down in the notes, but I'm not going to do it here. I'm going to say delta L because that's our angular momentum. And of course, instead of force, we've got torque. And time is time. Time is there. Time's something that we're all rushing around about. Okay. Conservation of angular momentum. For that to happen, for this to happen, then delta L, which is L final minus L initial, equals torque net times T. For this to happen, right here, for LF to equal L naught, What does this have to be? 0, right? So then all of a sudden LF equals L0, and we're back to conservation, cons of an angry mom. Cons of angular momentum. And that's okay, but we really want to talk about the impulse, so we can do a couple of things. We can say, all right, well, here's our delta L. We can divide it by our delta T, and that'll equal our torque net, which we can also alpha. I don't like that alpha. Let's do a better alpha. Like that. So our I alpha, and which we can also stick in our forces, right? R times our F net, or such, some such. I'm going to leave the net off there. Okay, times the sine of the angle between them. So that is a rotational impulse equation. Okay. All right. No external torques. That's what this is. Right here. No external forces or torques. And that sums up our mechanics, everything prior to fluid dynamics. So let's push all that off to the side, and we'll start doing fluid. First we start with statics, of course, but we're going to just talk about fluids in general. We've got the 4 phases, solid, liquid, gases, and plasmas. All right, so we're not talking about plasmas, even though, so yeah, don't worry about plasmas. Gases and liquids, we are both considering these both as fluids. So solids out. We're not doing solids anymore, so just liquids and gases. All right, those are our fluids. That's what we'll be totally working with. So we don't even need to worry about how tightly packed a solid is, rotationally bound. Well, I mean, I don't know if that's true or not. I can't remember the test. So tightly packed, rotationally bound. What do we mean by rotationally bound? It doesn't mean that the whole solid can't rotate. It means that the atoms or molecules, these little guys that are tied together, they're all sitting there hoping to stay with relationship to each other the same way that they've always been. They can't move about. So if we take another one and we put it right here, it can't roll. It can't roll that way. It can't roll that way. When we put it there, it stays there. All right. So they're rotationally bound. It can't move about the solid. Liquids, however, and gases are, whether they're tightly packed or not, they're rotationally free, okay? Same here, rotationally free. So nice. That's a good thing to think about. Liquids are also, they're both also linearly free. However, gases are particularly linear free. Liquids are, let's just say liquids aren't necessarily linear free. We can consider them as linearly free, but they mostly are just able to move left or right in relationship to other molecules. So this right here can't happen for a solid, but can happen for a liquid. So, and of course, we're not going to talk about those. All right, so density. Density is defined as rho, and that is mass per volume. And of course, mass is in kilograms, so that means, and volumes in three-dimensional meters lengths, so we have meters cubed. So kilograms per meters cubed. Let's just plug in force while we're at it. Or I'm sorry, force. Let's plug in pressure while we're at it. So we're doing pressure as well. That's a capital P. And it equals the force per area. And that's in newtons per meter squared. Area is in meters squared. But we have defined that to be 1 Pascal. So 1 Pascal is the unit newtons per meter squared. These are SI units, by the way. This is all the SI system internationale. So Pascal's principle. Pascal's principle at the same height, you might call it depth, you could look at it either way, in the fluid, the same height or depth, depends on where you're coming from. The pressure at one point is equal to the pressure at another point. So P1 is equal to P2. And the best way, and of course, at the same height and depth, these equivalences have to have a so over here we have a piston, over here we have a piston, and then our equivalent height or depth would be there, and so the pressure P2 is equal to P1. And we already remember that A1 over here, we have area 2 over here. So that's important. But these are connected. They have to be connected volumes of fluid. So there are some things that can go along with that. P1 equals F1 over A1. And of course that equals P2, which is equal to F2 over A2. And then we can amplify a small F2 the way I've drawn it. F2 would be small and have a large F1. So F2 is equal to A2 over A1 F1. The way I've done it. Okay, those are equal. And now F2 is less than F1. So good for us. This is the basis for hydraulics. And I have a feeling this is definitely on the test, so you might want to keep that going. Keep it in your brain. Okay, so gauge pressure. Why do I have such a hard time with this word gauge every single time? G-A-U-G-E. Gauge pressure. Anything G-A-U. It's always U before A, I guess, but whatever. So we call the gauge pressure PG. We call atmospheric pressure we call that PATM. And then we call our absolute pressure PABS. Now, we're going to measure this guy. The atmospheric pressure we can do nothing about, but usually when we're measuring a gauge pressure, we're measuring it in already atmospheric pressure. And then, of course, absolute pressure is whatever the pressure is absolutely. So let's look at P absolute for a second. In a vacuum, so we've got our P vacuum. P vacuum has no pressure. There's nothing there to push on anything else. So no pressure. Nice. Everybody's happy about that. You don't want to live in a vacuum, however. You need to have a little pressure in your life. But P absolute, then, in that situation, is 0. What are the units of pressure? Well, it's force per area, so let's get into that. Pressure units is a force per meter squared. So our absolute, I must have done this already because it's in pascals. Okay, I think I remember doing that. So good, now you've had it twice. Atmospheric pressure is simply the pressure from all the air above us. Pressing down on us. And then gauge pressure is pressure measured. So we can get into different things. We can say our P absolute is equal to our measured pressure at sea level when we do some measurement. We've got a measured pressure, and we're going to add the pressure of the atmosphere to get our absolute pressure at that point. That's the absolute pressure at that point. If we want to rearrange this, let's do that. Let's rearrange it a little bit so that we're seeing what we gauged. So we measure our gauge pressure. What are we really doing? We're measuring the absolute pressure at that point minus the atmospheric pressure. A manometer. So manometer is used, a manometer is used to measure pressure and there's clever ways to do it. Digital components, there are ways to do that, but let's fill some fluid in here. We've got fluid from there to there. We've got some height from there to there. And here's our fluid. Let's color it in. Fluid. And let's call it mercury. Let's use, should we use mercury? No, I guess we're not. We're not going to use mercury. So our pressure gauge is equal to rho times G H. Do I need to erase some stuff here? Times H1, that's the difference, and rho absolute, pressure absolute is equal to our GH1 times rho plus a constant, and our P atmosphere. You know what? I don't like this H1 situation or any of that other stuff. I want to do it as just H1. So because what we did in class is easier and simpler, and I like just H. So let's just do H. So our PABS is equal to rho GH1 plus our P atmosphere, which means PATM equals the constant. And it is a constant. So we like that. All right. What I was trying to do in the notes is show that we could have it go the other direction as well. So we could have it go the other direction as well, and we would have a situation like this, and this is minus h, and that's all I was trying to point out. Okay, so now we have minus h difference. H was positive here, greater than 0 here. H is less than 0 here. And we can do the same old thing, minus rho GH2. And that's pressure gauge. And then our P absolute is equal to our pressure gauge, which would be minus rho. So if P atmosphere is going to be positive, let's put it first. And then we're going to subtract off our P gauge, which is minus rho GH2. That's all I was trying to say in that ugly way. It wasn't a pretty way to do it. So we clean that up. Good. So Archimedes principle. Archimedes, famous for Eureka. I have found it in the bathtub. Oh, that guy. Okay, he came up with this apparently in the bathtub because he got into the bathtub and the water raised a certain amount. And so he's, and then, kids do that, right? And they call him genius, right? But kids do it all the time, and you did it when you were a kid. Did they call you a genius? No. What's up? So, the amount of buoyancy force is equal to the weight of the fluid displaced. And I almost made it through the whole sentence without messing up displaced. So our force buoyant is equal to the weight. I'm going to not do weight of fluid displaced. I'm going to do mass of fluid displaced times gravity. All right? Because that's basically what we're talking about. And so now that's fine. That's Archimedes' principle, and we went over it pretty well in class. So we're going to get to the density of objects, because a density of the object, again, is our mass per volume. And we've got some density things happening. we've got the density of the fluid, and we've got the density of the object. Now, if the density of the fluid is greater than the density of the object, then it floats. And that makes sense, right? And if the density of the fluid is less than the density of the object, then the object sinks. Now, does anybody know what SG is? I didn't write it out there. Oh, I did write it out there. SG is specific gravity. Okay, and all that is SG is equal to the density of our object, and it's the average density. It's the overall density. If you were to take all of the mass in the object and divide it by all of the volume, that's what you would have. Instead of just doing parts and pieces like we did with the balloon, right? We divided up the balloon into different parts and pieces. The balloon, the dense parts of the balloon versus the air part of the balloon. So we're comparing with rho water. Okay, so let's just write out water. And we always want to compare, that's our specific gravity. It's in relationship to water, and rho water is equal to 10 to the 3 kilograms per meter cubed. So that's our specific gravity. Let's do the last one here. If the fluid is equal to the rho of the object, the fluid's density may change at heights. Okay, it may change. Like I did tell you that water does get compressed as it goes down, right? Even though we call it incompressible, it does get compressed, and there are places where the density of the fluid might be the same as the density of your object. If you were to drop an object like that into the ocean, and there's a point where the densities are equal, that object will fall all the way to the point where those densities are equal, and then it'll sit suspended at that point. Okay, so sits in stasis or is suspended. In the fluid. All right, so let's talk a little bit about these with relation to the specific gravity. If water is the thing that we're comparing to, then and we've got our object in water, then if the specific gravity of the object is less than 1, that's a specific, it floats. If the specific gravity of the object is greater than 1, it sinks. And of course, it's equal. SG is equal to 1 when it suspends. All right, now this is all with relationship to water. Now you can have specific gravity in mercury, and your specific gravity in mercury is going to be different than your specific gravity in water. Okay, so that is something that could happen, and most things are less dense than mercury. It's fairly dense, so most things would float on top of mercury. So let's move forward here. We've got surface tension. Surface tension, the symbol for surface tension is gamma, and that's a force per length. So it's a Newton per meter. In units, the effect of surface tension is to contract the surface area of the fluid to be its smallest possible surface area. So we have a surface and we've got this fluid on top of the surface, and that area, the surface area, is minimized by the surface tension. Okay, so this is molecule to molecule of the same stuff. So let's call this water. So everything in there is water. And if everything is there is water, and this water is trying to stay together, it is meaning it's all the same, adhesive. Okay, this is a cohesive force. All right, good. So it's pulling it all together. Now, the next thing that we've got is capillary. Let's treat it. I was abroad, and I was working in Egypt, actually. And Egypt, I don't know if people know this or not, but it was one of the British colonies at one point. Anyway, British people live and work there, and they speak English in a very British way, much like India. And so when they say capillary action, when I was there, I was doing engineering, but it doesn't matter. We were working with capillary action. It was capillary action. So there you have it. And we can talk capillary if you would like. And capillary action is a little bit different. We don't have surface tension. We don't have a gamma for capillary action. We don't have a symbol that represents this is capillary action. But what we do know is that capillary action would be the action where this drop of water on this surface wants to spread out, okay? So it wants to spread out, and there's a fight between this capillary action and the surface area contraction. So they are fighting each other. So the water, well, I don't know, maybe it's wax. The wax doesn't have a very good attachment to the water, and so then it's able to bead up more. I don't know if you guys have noticed, you drop some it's unprotected wood, for example, and you spill water all over it. That wood will absorb the water, and the surface area, the surface tension, the surface tension isn't allowed to hold it together, and it will not bead up. The wood will absorb it. At any rate, this beading is a fight between the surface tension and the capillary action that happens. So what is that fight between? It's really between cohesive force of the surface tension and the adhesive force of the capillary action. So it's an adhesive force. Now so really there's not, you can take a pipette and you can put it in some fluid, and that pipette will be narrow, and that fluid, it'll often have a little meniscus there, and this fluid will go up into the pipette, and it'll climb up the pipette, and it'll climb up a certain height h. All right, well, that just means that it is able to take our center of mass, whatever that volume of stuff is, a certain height h. In fact, here, let's do it. Let's do it properly. We'll measure from the center of mass. Okay, so h is the center of mass above, right? If you want to think of it that way. It doesn't matter if you think of it halfway or the full thing. None of that really matters, because what you really need to know is that your gamma is your surface tension, and your contact angle, which we talked about in class. That's this angle. So we've got our contact angle. We've got our density of the fluid. Fluid density. And we've got our radius of the, so this is our pipette, and it has a radius half of the diameter. So our radius is equal to the diameter over 2 of the pipette, usually given in the diameters, right? So that's just the radius of tube. And then we know G. So what we can do is we can say, okay, our capillary action will happen. It will draw, because the adhesive force draws the fluid up into the pipette. It will draw it a height of 2 gamma cosine theta rho gr. Now, whether that height is all the way to the top or to the center of mass, I don't think matters. You don't care. We didn't derive it, so seeing as we didn't derive it, I'm not going to worry about whether it's halfway or the full h. We really don't care. Getting the h is all that matters. This is g. G equals g. Okay, so our contact angle. Let's talk about that a little bit. Our contact angle could be, depending on the surface, so we'll have surface 1 here, and we've got fluid 1. Fluid 1. This contact angle is quite large. Okay, that's our theta contact angle. And then we can come over here to surface 2. And on this surface, we've got this very slight beading happening, and our contact angle is something like that. And so that's our contact angle for 2. This is our contact angle for 1. So when we go through and we figure out the cosine of something, the cosine is more, it's higher. It can only range between 0 and 1. So it's closer to 1 when this contact angle is larger. Okay, so our adhesive force for the capillary action gives us a higher cosine of theta is greater in this situation than this situation. So which of these surfaces are going to have a greater h? Well, obviously, you can even tell right here. The distance that this thing spreads out, it wants to attach to the surface. So if it wants to attach to the surface, it's going to give you a higher h, and that just totally makes sense. So it's directly proportional to our cosine of theta. It's directly proportional to our surface tension, which is kind of counterintuitive, but indirectly proportional to the density of the fluid and the radius. So as the radius gets larger, our h goes down. So these proportionalities for that equation are important. You want to be able to say if this goes up, this goes down, and vice versa. So here we have fluid dynamics. I think we're going to have to do part 4. So we're going to go into fluid dynamics in a bit. So I'm going to put fluid dynamics, and we will carry on from there in, let's see, we've done part 1, part 2, this was part 3. So next time will be part 4. So fluid dynamics, part 4, physics 1111, coming up. We're going to do it in a second.